So is there any questions about Shor's algorithm before we move on? So Gruber's algorithm is very short, although if I need to go detailed, then getting long, but Gruber's algorithm can be done shortly compared to the Shor's algorithm. But once we get the Gruber's algorithm, we're going to talk about the quantum error correction, and at that point, it's a different issue. So I want to make sure that everyone understand the Shor's algorithm. So is there any questions about the Shor's algorithm? Yes.
We are apply this pure algorithm to it works how than
How much faster is Shor's algorithm compared to the classical algorithm?
그냥 컴퓨터에서 우리가 시뮬레이션을 보고 실제 양육 컴퓨터에서
So if you want to run Shor's algorithm on simulator, that means you have the list of value functions already. So you have so I'm saying that it's impossible to run the Shor's algorithm on the simulator unless you know all the answers already. So I think it's pointless to compare the speed here. So, but if you assume that it's okay, the question that whether which one is fast, or maybe in that case too, it's pointless. So in the simulator, it runs on classical computer. On the quantum computer, there are many things to consider. One is the error correction and the quantum error, and also there is a classical computer attached to the quantum computer in order to get the result of the measurement outcomes. So you cannot really tell which part is faster and which are not. So okay, so what do we need if you want to break the RSA code using this Shor's algorithm? You need the oracle. So you need the oracle. And what does this oracle says? It's the modulo of sorry, it's x n, where a is not 0 or 1. So if you want to implement the Shor's algorithm, in order to break the RSA, or in order to vectorize a large number, you assume that you know this function already. But if you know this function already, then there's no, it's pointless to find the period of the function, right? You can actually get the period by looking at the list. It's because we are using this quantum oracle because it's impossible to find an entire list. So basically there's no quantum computer that you can implement Shor's algorithm in practical level because it has so few quantum qubits, so that it can break the practical RSA code. But in a simulator level, I think you can do it because nowadays IBM has 200 qubit simulator, I think. So in theory, you can do it, but I think it costs a lot. So yeah, the answer to that question, comparing the speed of real quantum computer and simulator, I don't know, because nobody knows. The main problem when you have a large number of qubits is the quantum error. It has too many errors. So maybe it takes more time to get a correct error than actually get the computation done. So that's the main problem, making a large qubit quantum computer. So, well, I can tell you some stories about it. So far, the most effective, most reliable quantum computer is a based on superconducting qubit, and it needs to be cooled down almost equivalent to the sub-zero, sub-zero temperature, and also it has to be flat. So if you want the large qubits, then it has a large surface area. So it's really hard to get the large surface area to be cooled down. But if you have like a three-dimensional object in a small volume, then it's relatively easy to get it cooled down, contained in a small container. But if it's a flat, then you need lots of big machine, you need big container to make it cool down. And I think that's the fundamental issue here, because if it's not cooled down almost to the absolute zero temperature, then it has too many errors, when you take the measurement and do something. So, so the people are working on other material to substitute the superconducting qubit, such as diamond effect or optics. So none of them actually got successful yet in a level that it can make a quantum computer. I don't believe that someone actually claimed that they made a quantum computer based on other quantum material. I don't think it's yet. I don't think it has a functionality equivalent to the superconducting qubit yet, but maybe not. So anyway, yeah. So sorry for not answering the question. Any other questions about the algorithms of Shor's algorithmic part? Okay, so I'll just let's move on to the Grover's algorithm. I think that's going to be short. Sorry for today. I'm not going to write on the pad. I'm going to use the old notes here. So well, if I need to explain it more detail, then I'll use a separate note. Okay, so what is the Grover's algorithm? So that's another algorithm that people always mention when they talk about quantum supremacy. So it's an algorithm that claims to supersede the speed of the classical algorithm. It's about the search function, the search function. It's about the search function. Suppose that you have a list of characters or strings, and you want to find some specific characters or strings of characters, then basically there's no way you can do it fast in general. Well, maybe there are many protocols of searching that works better in principle than the other types of data. It depends on what the data look like. But in general, if you are given with the general data set, there is no algorithm that is better, way better than the others. So basically, there are no way you can find faster than just looking from the top to bottom. So what is the search function? It's the function that gives you the truth table. So if you found that table, if you found that character, then you get 1. If it's not found, you get 0. So it's a 0-1 function. So I want to have, suppose that this function is given, I want to have a faster way to find my A. This A is what I want to find. So what is our oracle? So again, I'm not saying that we can make such oracle. We are assuming that this oracle can be implemented somehow without knowing this function itself. Okay, so if you know the function itself, then we know what A is, right? So we're assuming that we don't know it. Among these zeros, there are only one value of function. We want to find when this happened. That's A. So this oracle gives you input and output. So input is n number of qubit, output is only 1 qubit, and it makes the input the same, but output you change it to plus f of x. So let's design a circuit, and it's kind of a bit complicated. But design the circuit, not the design, but the way how it works, way how the Gruber's algorithm are designed is a little bit complicated. So I'll introduce some other operators. So first operator is V. So V is changing the base state x to plus x or minus x, depending on f of x. So if f of x, if x is not a, then f of x is 0, so it keeps the x. But if x is a, then it returns minus a. Okay? So how do we make such operator? It's it's not designed with the multiple of x and z gates such, but you can define V ideally by identity operator minus this operator. So you have a Canberra, so only splits the A when input is A. So otherwise, always 0. So the identity operator works. And let's take the one type of special quantum state, phi. So it's basically the superposed state of all the possible base state. And we're going to make another operator W given by this. Okay, so phi is also a special type of qubit state, and if you take the Ketra of these state, then you can get an operator. It's a unitary operator. It's another unitary operator. You can compute that. And also, I'm not saying that you can make this operator using this X or Z gate or such, but let's say this is our operator we can implement on our circuit. So let's think about what does this operator do. So operator V is sending A to minus A, obviously, that's the definition. And what happens to phi? So when you feed your operator V onto phi, then just simply put that in here. So put that into the definition here. Right. So maybe I should write something on here. So everything is the same except for the base state A, right? So you can say that here there are 2 to the power of n state, but except one, everything fall into this case. So this is after you apply v on here, there are only one a state. So the coefficient remains the same. So you get all of a states from 0 to 1, which implies 2 to the n. But except for a, and what happened to a? A becomes minus a here, right? So you can rewrite this state as if you get a, you have a in this summation, and then you subtracted it twice, so that you make the coefficient of base state a minus. So that's what it says. So you have original state with the coefficient, and you subtracted one base state twice here to get only that base state as a coefficient of only that state to be minus. Okay, so that's what happens when you apply v onto v. And let's see how what happens when you apply w. So when you apply w to v, what is w? It's just this. So it happens the same thing, v. Then when you apply w to a, then look what happens. So here, your w a is same as 2 v a minus a. So what is this? So it means that you only get the a base state, right? So 2v times 2 to the n over 2, 1 minus a, right? So same thing. So you get some coefficient here, but so that's why you have coefficient, but you are, yeah, so just a is there, sorry. So a is there. So a is there, so you get this coefficient minus a. That's the working of w on a. And now let's think about, why we're talking about phi. So if you take the inner product between a and phi, that's 1 over 2 to the n over 2. So here we are dealing with the lots of characters in the string. Or if you have a small number of characters, you can't just use your classical computer. Let's say you have a 10 list of character. It's a 2 to the power of 10. All the possible ways that you can get is 2 to the power of 10. Only 1,000. You can just go through 1,000 lists to find which one is yours. However, if you're looking at like hundreds of thousands of strings, characters, then it's impossible to go through all the list. So we're assuming that n is really big number. But then if you take the bracket a and b, it's 1 over big number here. So you can see that it's almost equals to 0. So what happens when you think about this as vectors? So bracket of a phi is measuring the cosine of angle between these two ket vectors, a and phi. If they are almost equal to 0, that means these two vectors are almost perpendicular. So I'm not saying in principle they're actually in perpendicular position because it's just the representation of quantum state, but you can visualize this geometrically so that the rest of the argument is how the rest of the argument is designed. So let's assume that a and b is perpendicular, and let's take one vector, and well, there are infinitely many vectors, but let's assume that what I indicate by a perp. So here, the shape O is a perp, meaning that it's perpendicular to a, or orthogonal. and it lies on the plane spanned by these two A and phi vectors. So it's the real perpendicular vectors. Phi is almost perpendicular to A. Okay, so A, let's say, did I indicate A? So maybe A is this one. So let's say A is this one, and phi is this vector. I said it's almost perpendicular, not exactly perpendicular. So I can take a plane, two-dimensional plane, spanned by these two vectors, say not A vector, the ket A, and this A perp is one that actually perpendicular to A. Okay. Now let's work on this vector space, work on this plane spanned by A and phi. So everyone understand what we are talking about. We are looking at two-dimensional plane where these two vector lies in. Okay, so think about V here. What does V do on A and phi? Go back to here. V is inverting A. And what does V do on phi? It does this. So it takes the phi the same, but it inverts the A with the small coefficient. So you can kind of ignore this part because it's a very small number. The coefficient is very small number. So you can kind of assume that this V is taking the phi to phi and taking A to minus A. So in some sense, it's same thing as reflecting the plane through the phi direction. So here's the phi direction. This is the phi direction. What V does is reflecting across across the perpendicular direction of A, hyperplane perpendicular to A. So let's see. If A is applied to V, it goes to here, right? Minus A. So yeah, there's so I get a little bit confused with this. Which one I should take as approximately 0? Which one I shouldn't? But let's take it. Let's take it this way. So V is a reflection across hyperplane perpendicular to A, which means that it reflects along this A perp direction. Okay, so it reflects across A perp direction. So yeah, I think so this is not A, sorry. So this is A. This one is A. That's why I got A perp on the perpendicular direction. Sorry. So that's why I got misunderstanding. So anyway, so A goes to minus A by V, so it's actually reflecting. And how about W? So W is sending phi to phi, but A to minus A, because we can ignore the coefficient this. So this is almost 0. So we can say that W is reflecting across to phi, across to phi here. So W is a reflection across something perpendicular to phi. So phi is here, so wait. Phi W is phi. Right, so W keeps the phi and it reflects across. I think there's a typo here. So W is a reflection across hyperplane, parallel. I thought it was a perp, so it's a parallel to phi because it keeps the phi direction, but the other direction, A, is reflected to the negative direction. So it reflects A direction. Okay, so you can say that V and W are both reflection. It's the same as meaning of the reflection. Now, what does WV do? When you apply V and W successively, it's actually a rotation. So here's I can explain more with a separate. Maybe I can use. But let's use the bottom here. So use this space. So when you have a reflection, let me explain this here. Or let's use x and y coordinate. So here x and y. So I have a vector. If I reflect around x-axis, then I have here. That's my v1 here. So, and then when I reflect around y, what happens? Here, v2. So what's the effect of having two reflections applied to the same vector successively? I reflected v 180 degree to the other side. So that's because x and y are 90 degree perpendicular to each other. What if I use different directions, different hyperplane, different lines to reflect? So for example, let me have another picture here. Let's say I have this vector and this vector. So that's let's say call it A and V, just to match with our discussion before. And I have vector V. Or maybe I should, yeah, well, anyway, so take it this way. So let's see, maybe A perp. I want to reflect across A perp. So here I get after one reflection, and then I reflect across the phi vector. So then I get, let's see, right here. So if you compare the vector v to vector v2, what happened? You rotate v to v2 in how much angle? You rotate by twice the angle between A perp and phi. So if you say this is your angle, then after reflecting across two vectors, you get rotation of original vector to. So it depends on which one you do first. If you do the A perp first, then you reflect to the counterclockwise direction by 2 times of theta, twice the angle between these two vectors. Okay, so that's a basic principle. So let's go back to our discussion here. So when you apply V and W, you keep to the vector V, you keep rotate the vector V by 2 times of theta, where theta is the angle between these two vectors, V and A perp. Okay, so this V and A perp is the axis that we're going to interpret V and W as a reflection. So we're trying to measure this V. Okay, so how much is this V? So as I said, this A and phi are almost perpendicular, and A perp is perpendicular, actually perpendicular to A. So therefore, A perp and phi are almost parallel. So that means theta is almost equal to 0, but not 0. So there are still some angle between them. But if we take this operation V and W successively to the ket vector, then we end up having if you apply n times, we end up having phi, cat phi, rotated away from the perpendicular direction of A by this much. So 1 is from the original position. Each time it rotates, you add 2 theta to the angle between phi and A perp. So after n successive application, you get this much angle between these two vectors. Okay, so the phi is not phi anymore. Cat phi is changed to different. So what we want is we want to apply it so that the angle is close to pi over 2. So this is close to pi over 2. Why? Because then we know that cat phi is almost equals to A. We want to get almost equals to A. So how do we guarantee that it's almost equal to A? Well, you can get it by lots of iteration. Right? There's approximate number of you have to apply um, based on the size of your strings. But let's say it doesn't grow exponentially because every time you apply your rotation, you are let's see, so many times. Well, okay, so this n is actually equals to the number of strings, number of qubits here. So almost equal. Well, let's think this later. So anyway, so n here is the number of qubits in x and here. So you know the number, and so let's say n is 1,000. So you have 1,000 list of characters in your strings to find which one is yours, and you apply your quantum this operator 1,000 times, but it's lot less than searching this 2 to the power of 1,000 list of possible numbers. So it's doable, but once you've done that, what happens is it almost equals to pi over 2 after the successive operation. So then after the 1,000 operation, you measure the phi, the vector, the cat vector, the changed after the 1,000 operations. You measure it. And ideally, it must be almost equals to A. Right? So the measurement outcome should be the same as A because there's no other vectors nearby A than the A itself, because A already have this each digit of the string A is discretized either 0 or 1. Each character of the string is either 0 or 1. So you have, if you are enough close to the phi, enough close to A, then there's no other than the character A than itself. So your measurement ideally must be equals to A. But there should be possibility that your measurement outcome is not equals to A. Then you redo it. Well, when do you know when you got the right string A? You just simply query your function. You query your answer A, the possible candidate of A, to your function, whether it spits out the value 1 or not. So you got the measurement outcome of your changed cat phi, and then you put it into a function. If it gives you 0, then it's not the answer. Something got wrong. So you redo it again. Redo it the 1,000 operations on the function, the cat state phi, and then you do the measurement again, and then check whether you got the answers by querying the functions, and you keep doing it. So it's a lot faster than doing it 2 to the power of 1,000 times searching. So that's why it's a famous algorithm that supersede the classical algorithm. So it's a kind of simple, but the problem is, um, you see, it's not really efficient. And I mean, what I mean by not efficient is that when do you really need to, search for this thousand list of characters? Like if you have to look for a thousand list of character, what's the practical use of this? So people haven't. I mean, this is an ideal situation. I mean, it's a situation that could this quantum algorithm could supersede the classical algorithm, but people doesn't really found it's a practical application. And also, the problem is it's very complicated to implement this W and V, and also fine tuning these success operators because you at least need lots of operations applied to the same qubit. And once you have this many operations, then there are many chances to have errors. So it's a lot harder to correct errors. So, and also, but it's because there's no quantum computer, people haven't found any real effect on how effectively can this algorithm find the character that you want to find. So, um, so I've seen some paper about this Gruber's algorithm, but not many of them got uh, you know, popular. So you can find some of the research based on the Gruber's algorithm, but it's not as popular as Shor's algorithm or other application of quantum algorithms. So anyway, so this is basic idea about Gruber's algorithm. Let me know if any part is not clear, so we can think about this together. Mm. Okay, let's think about that part. So, actually, there is a note here. All right, so we know that if you take the dot product or inner product between two vectors, you get cosine of angle between these two vectors. So we know that it's almost zero. What happens is, you know that sine theta is almost theta if theta is way smaller than 1. So it's almost equal to 0, then this theta and sine theta is almost equal. So I can rewrite this as sine of 2 pi plus r or minus r, doesn't matter. So minus r here. So why did I use R here? Oh, I used it for indicate this angle. It's R. Gamma, maybe. So since we have a sine something almost equals to 0, I can assume that pi over 2 minus gamma is almost equals to 0. And when I have such a situation, then I can say this sine value is almost equals to the theta value, pi over 2 minus gamma. That's my theta here. So that's why I get this theta here. So let's take this as our theta, and let's see. If I take the sine theta, why sine theta is all right. So sine theta, yeah, it's the same thing, right? So sorry, so it's the same thing. Sine theta is equals to cosine gamma, right? So, and instead of looking at it almost equal to 0, let's just compute the exact value of the dot product, the cat bracket of A and B. So 2 to the power of minus n over 2. Right? So then, since this is small number, I can assume that B theta is equals to 2 to the minus n over 2. So let's see. So I think maybe not n is the same n. So let's think about how many times should I rotate theta or rotate the cat phi by 2 theta in order to make it almost equals to pi over 2. So if I, let's say, E2n theta, then it is almost equals to 2 times n 1 over 2 n over 2. And if I want that to be equals to pi over 2, then n is 4 pi 2 to the n over 2. Oh, sorry, so I made a mistake here. So yeah, actually it's worse than I was thinking. So what happens is the number of rotation that you need to perform in order to get pi over 2 angle is actually lot bigger than you need. It's pi times this much. So your operation is the number of operation you need to perform is down to the square of the number of operation when you use your classical computer. Because this is almost, you just ignore the constant pi and minus 2 on the exponent. It's, let's say this is almost equals to 2 to the power of n over 2. That is square root of 2 to the n. So if you use the classical computer, you need to, there's no way in principle in the worst case scenario other than performing the currying the function 2 to the n power of times, right? That's a lot. But the Gruber's algorithm says if you use this algorithm, you can just do it with a square number of that, in a square number of that. So, like if you have a 2 to the 1,000, maybe 1,000 is too much. So maybe if you have a 2 to the 100, need 1,000 number of times to function in a classical computer. But in the Gruber's algorithm, you can do it by 32, 2 to the 5, 32 times in order to get the result. Of course, this result is not 100% guaranteed. So you cannot really compare which one is more effective because the worst case scenario, which could happen, is that you could end up doing the same number of times of calling the function with the find the actual value, but then it becomes actually worse than the classical algorithm because considering all the, the costs for the quantum computer. But anyway, in principle, it's better. In theory, it's better. So that's why people think it's one other application of the quantum algorithms. So sorry for I mistake the n as a number of the same integer n. I put it in here. That's not the same integer. This is somehow some other number n. So any other function? Any other questions? Well, shall we talk about the quantum error correction a little bit? Oh, you have a question. Large n? That's a number of operation you have to apply to the cat phi in order to make it pi over 2 angle between phi and a per. So our purpose is to rotate our phi, cat phi. Okay? So by applying this VW operator. Okay, so n is the number of operator, a number of times that you have to apply the operator in order to get the desired state. So once you get the n number of operator done, acted on the phi, then you get the vector, which is almost parallel to the ket A. And if you're sufficiently close to A, then there's no other vector, no other base state closer to A. So once you measure it, then you always get the ket A, the same output of A. So that's what we are expecting. So you need to apply this number of n. Any other questions? Okay, well, we don't have much time left, but we can talk about a little bit about the quantum error correction. This part. So it's called QEC, but I'm just introducing the quantum error correction basic ideas of why we need this. It's because of instability of this quantum state, and it depends on the quantum material, of course. So unlike our classical computer, quantum state or quantum material stores its states in a very short period of time. So it will collapse after, so it's also probabilistic that whether it collapses to another state or not. But anyway, the on average, the length of time that the quantum material stores the quantum information is very short, especially for the superconducting qubits. So we need, so and also that within that time, it's impossible to get all the operation done, and also including the measurement. So and also after each time, you have chance that you get an error. So let's talk about the quantum error first. Quantum error are caused by decoherence, meaning that the quantum state collapsed by itself because it's not stable. And the quantum error is happens when you apply the quantum operators. Quantum error happens when acting on operator, and it can happen at the measurement stage. Measuring qubits. Okay, so here's the story. We don't know whether quantum error actually happened or not. Okay, so all we can expect is that things go by our calculation. So for example, what's the simplest calculation? So what if we initialized our quantum state to 0, then after some period of time, when I take the measurement, what I'm expecting is to see 0, okay? Then you can say, okay, no error occurred. But if you find that measurement outcome is 1, then you may see, oh, there's something wrong between this period of time. So when I take the initialization and the measurement, there's some collapse going on. But the question is, we don't know whether it was occurred during the waiting time or during the measurement or some other reason. So we don't know the reason, we only know the result. So what we can think about the quantum error is the following. If we are expecting the outcome as 0, but we measured 1, then we kind of assume then that unexpected X gate were applied to the state. So this is unexpected gate. Okay. So in that case, we say the X error is occurred. Okay. So simply, or X error. So X error is that something that when we expect to see 0 or 1, the outcome was the opposite. That's X error. Now, the same thing could happen in similar fashion that I want to expect the plus, but the measurement outcome after let's say, taking the Hadamard here, the measurement outcome, if it was a positive, then the measurement outcome should be 0, but it was 1. But then what I could expect is that there's something going on here, which is that gate applied unexpectedly. So we have, this is somewhat unexpected. And we call it Z error. Okay. So in principle, when we say we correct the error, we correct the quantum error, it means that we either correct the effect of X error or Z error. No other errors are our interest, because In principle, like what is the quantum state, a one qubit state? In principle, it's alpha times beta, like this one. And you could have, well, maybe after normalization, you have A 0 plus B e to the I 1, where A squared B squared equals to 1. That's uh, the flow state of the quantum one qubit state. Now, what we are expecting, I mean, in principle, what could happen is that these A or B could change its value a little bit. So that's, affects to the measurement outcome. And also, this phase could be shifted. So all this value could be changed after some period of time. And even after, right after the qubits are prepared, you don't have a guarantee that it stays the same, these values stays the same. But what we actually could measure, what we actually could detect is whether 0 is turned into 1 or 1 is turned into 0, or after the Hadamard gate, whether a plus ket is turned into minus ket or minus ket is turned into plus ket. So when this X gate is occurred, we call it bit flip error. Because it flips the ket 0 and ket 1. So it just flips the bits. And that error is called the phase flip error. Because it flips the phase theta to theta plus pi. So it just flips the negative of the exponent of exponential here. So these are only two errors that we are interested and that we can actually correct. So what's the purpose of error correction? So what's the goal? The goal is detect the X error and Z error. Now, why do I say detect, not correct? Because we can only detect, not correct, the quantum errors. So, okay, so usually when you're dealing with the error correction in the classical computer, when you detect an error, then you should correct the error. Let's say there is a memory that has an error correction function equipped it with, and it's actually a little bit more expensive. Then what happens is that it detects an error in some memory space, then it corrects it to the original or correct value by changing 0 to 1 or 1 to 0. However, when you're talking about the quantum circuit, let's say at certain point of the quantum circuit, let's assume that you detect an error. Okay, this shouldn't happen. Maybe X error occurred. You cannot throw in X gate inside your quantum circuit to correct it. Okay, so because quantum circuits are designed in the first place and then run it almost instantly, you cannot just you cannot insert new quantum circuit while the quantum circuit is running. So what you are doing here in the error correction is you simply detect an error and then keep it to yourself and then see the result, and then you somehow backtrace your result so that whether your computation is correct or not by assuming that such error was occurred. So here's a simple idea of what's going on. So because it's important, why you have important to understand the quantum error mechanism here. So okay, here I'll just say the X error as a wiggly box here. So this is an error. And at this point, you detect an error. So I'll talk about how you detect an error next time, but let's assume that you detected an error and there's no other circuit, no other operator in the circuit, just just a plain circuit without anything. So you got this. Now what happens is, even if you detect an error, you don't throw your circuit or operator or gate into your circuit to correct it. So you just leave it there. Just detect. I mean, even if you detect, you cannot detect while the circuit is running. You almost get the entire information of your existence of errors and the result almost at the same time. So okay, so when you run the circuit, the information that you got 1 as an output and you had X error in your circuit are gathered at the same time. So you have to interpret this as, okay, so I got 1, but it says X error has occurred. So therefore, the original state that I was looking at was 0. So this one is because the error X error was there, but the actual circuit indicates that it's 1. It's 0. So this, in some sense, is corrected. So now, let's think about this way. So how about I get the same detection? I got the same detection here, but measurement outcome says 0. So I got detected X error. The measurement outcome is 0. So there are two possibilities. Okay, um, so there are two possibilities. One is that if I'm sure that my error correction is correct, so here again, your error correction could fail. There's a possibility that error correction itself could fail. I'm not saying that error correction is 100% accurate. So in this case, possibility is 1, the error correction failed. Okay, so you detected an error, but it's not really an error. And another possibility is that there is an error, you didn't detect it. Well, that's the same question here as the first possibility, same as the first possibility, but there's another possibility that you have an error at the measurement stage. So here is a measurement error occurred. Well, so in principle, if you think that measurement error occurred, then it's the same thing as measurement has 100% accuracy, only that we didn't detect it. So therefore, you can also throw this second case, the second possibility into first case, so that you didn't detect the external error occurred just before the measurement. So, well, that's basically the same situation as the first possibilities here. So here's the thing I want to conclude. So before we go through lots of algorithms or lots of schemes of error detection, the error correction, quantum error correction, could fail. And so that's the first thing. So quantum error correction in general can fix So I'm not that it's really fixing the error, it can detect, which same as detect an error of certain size. So what I mean by size is that if you adopt your quantum error correction, then it has certain size of a qubit that it can correct an error. So for example, if you want to correct one qubit error, then sometimes you need 5 or 7 or a lot more than that, qubit, physical qubits, for example, 10 qubits. So physical 10 qubits are required to make one qubit error detected or fixed. So, and the other thing that I want to talk about, um, yeah, so maybe, okay, so I want to conclude with this. So quantum error correction does not really fix an error. It detects. So how do you find out your error correction is correct? You don't find out. So you have to believe that your error correction your error correction worked properly, and then you can see the result and then take that as a correct result and then try to your problem and apply to your problem to solve your problem. And then if it doesn't solve it properly, then okay, maybe it was because of the error correction failed. I got the wrong answer. So you have to try it again. So your error correction raises your chance to get the correct answer, but it doesn't give you 100% accuracy of your error of your answer. So it's important to have. So it is important to have high, or say not high. Let me put it this way: efficient error correction scheme. So what I mean by efficient is there are many ways to measure efficiency. One is that, as I said, if you want to correct one qubit, you may need several real physical qubits. So you want to have as small number as possible for encoding a one qubit in your quantum correction, in error correction. So that one is one efficiency that you can achieve to get as small number as possible to get one qubit coded in your error correction. And the other is about the failure rate. So you want your error correction to be your error correction could really fix the error or detect an error as much as possible. So you have to make a simulation. You have to run the simulation over and over again using the simulator. That's where actually the simulator comes in, not in a real quantum computer. As I said, in a real quantum computer, you don't really know whether your quantum error correction worked or not because there are many, because the output is the only thing that you have, because you never know what real values are. So there's no the answer sheets here. So there you have to use your simulator to find out how efficient, how accurate your error correction scheme works in the quantum computer. So that's one other thing that you measure the efficiency of error correction code. And the thing that people are working with the error correction is, of course, they want to implement into the real quantum computer, and that is necessary and really crucial to have one, at least one. But once we have the good error correction code, then what they're expecting is, okay, that's not the error correction rate is not that high in principle. Okay, so let's say I want to have error correction failure rate as close as 10%. So that means only 10% get failed, other 90% accurate. But that's not really, high enough for some cases. So what they're doing after having such error correction is that they have a layer of qubits to encode into actual qubit. So here's the pictorial way of describing it. So let's say you have one logical qubit. So logical qubit means that it consists of lots of physical qubit, real qubit, to encode one qubit information. So then it is actually consists of lots of qubits, right? Physical qubit. But then you only get the 10% failure rate. I mean, not only the big failure rate, like 10%. But then you don't need to use the physical qubit to encode one logical qubit. Each of these qubits that makes up the logical qubit could be another logical qubit that each one can be consist of much more physical qubit. Well, maybe it's same as size of this one. But if you combine all of these logical qubit, then it's the square of the size of the one logical qubit in principle. So you have layers of physical qubit, or maybe just one layer, but layers of logical qubit, so that you get achieve a higher accuracy rate than just having one layer. So that's a basic idea of how the quantum error correction code works, and we'll kind of talk about early quantum error correction code from 5-qubit code, 7-qubit code, and then my goal is to introduce you the surface code, which is known to be the most effective quantum error correction code, and then try to understand how the surface code works. All right, so as I said, there's no class on Friday. We'll meet on Wednesday. I try to post the video for the Friday class to make up missing class. All right, let me know if you have any question. I'll see you on Wednesday.